Okay, good. So today I'm going to return to the example that I looked at yesterday at the end. We're going to go over some of the calculations, and then we're going to try to generalize this to describe a method for calculating the homology of the image of a mapping. And necessarily, some of what I do is going to be slightly, probably a bit quick. I mean, I'm going to ask you to take in a lot of mathematics, I think. It's reasonably well explained in the lecture notes, and I'm happy to talk about it afterwards with anybody who wants to ask any questions. But I think the most important thing is to keep the example in mind. That if you can hold on to the example and make some sense of the concepts in the context of the example, I think then you're in a very good position to follow the lecture. So we begin with this picture. If you remember, we have a map. Well, I'll put it up here. We started off with f of x, y was x, y cubed, xy plus y5, and then I made a deformation, f of f sub u v, x, y cubed plus u, y, xy, y5 plus v, y squared. And for suitable values of u and v, you have to choose the values of u and v a little bit carefully, but if you take suitable values, you get this picture. So the set of pairs of points mapping to the same image is a circle, or, well, is topologically a circle, and it has an involution, because the involution simply exchanges pairs of points. So, for example, here, the pair of points PQ is exchanged with the pair of points QP. We just interchange the order. That's the action of the symmetric group S2 on the space of pairs. So that action of symmetric group is going to be very important. Let me record the fact that we have this symmetric group here. So I know the picture will start getting a bit overloaded. So the symmetric group S2 acts on D2. Notice, actually, it's an interesting point. The symmetric group does not act down here, because although most points on this double curve, which is the image in R2, most points have a single partner point. These 3 points each has 2 partners. P is mapped to the same point as Q, and Q is mapped to the same point as R. So there's no way of defining the involution or the S2 action here. You have to go up to here to define it. That is, this is contained in R2 cross R2. And actually, we introduced the space D3 of triples of points having the same image. I'll just put them in so we can kind of list them like this. There are 6 P, R, Q, P, Q, R. That's 2 triples. Q, R, P, Q, P, R, and R, Q, P, R, P, Q. So there are 6 triples here corresponding to the 6 different orders in which you can write the 3 points P, Q, and R. And we've got the symmetric group S3 acting up here, permuting permuting the order of the copies of X, or the copies of R2. Sorry, the diagram's a bit overloaded now. And there's a projection from here to here. There's a projection from D3 to D2, which I call pi 3. And all you do is you forget the last copy. So D3 is contained in R2 cross R2 cross R2. D2 is contained in R2 cross R2. And to go from the top, from D3 to D2, I just forget the last copy. So I map PRQ to PR. And PQR, I map to PQ, etc. Okay, so it's quite striking that these 3 points, 1, 2, 3, they all map to the same point in the image, but in D3, we get this point sort of 6 times, right? It's an orbit of the symmetric group, S3. All right, so all of that information, somehow, we're going to try to make use of to get some understanding of the homology of the image. And at the moment, I don't make any attempt to draw a picture of the image. So let me just put question mark. Right. Okay, so let's be a bit more general now. So I'm going to define dk. So now this is f from x to y. Any map of topological spaces. So I'm going to define dk of f as follows. Well, to leave a space here, I'm interested in k tuples of points in x to the k, ordered k tuples. I want them to be different from one another, xi different from xj, if I not equal to j, and I want f of xi equals f of xj for all ij. Okay? Now, if I do that here, I get everything except for the orange points, which are the fixed points of the involution. Maybe I should give them a name. These correspond to the points where f is not an immersion. What shall I call this? ST. This is the pair SS, and this is the pair TT. Well, if I want to do anything algebraic, I really want closed sets. So I take the closure of this. Okay? So that's more or less the definition of the space of k-tuple points. And you can, of course, do this in algebraic geometry or in analytic geometry, because what you're doing is taking the variety defined by simply asking for this equality and removing some of its irreducible components. The irreducible components which are there for stupid reasons, because, of course, if I take the same point, then I have the same image. So we just remove some of the diagonals. But you can define this, so you can define this in algebraic geometry, or you can define it just by set theory, in topology. And it makes no difference, really. And there's a tiny inaccuracy in what I'm saying, because when, in the case where we're talking about something zero-dimensional, which is like D3, then we have to use a slightly different definition. And I'm not going to go into this now. Instead of describing how one gets over this small problem, which one can do, instead of describing it, let me straight away write down how you get equations for these spaces. So there are actually 2 ways of getting equations when we have a map germ of corank 1. So that's the only case in which we can really say anything sensible about these spaces, or at least up to a certain point. There is a remarkable theorem of Kevin Houston which says something sensible when the map has corank greater than 1, but that's not within our reach. That's quite hard to understand what's going on there. But let me assume that f from, well, I'm going to talk about maps, real or complex. We have to talk about complex sometimes because everything becomes simpler. And I want n less than p, and I want corank 1. This means that the dimension of the kernel of the differential of f is 1. So that's the situation with this map here. The dimension of the kernel at the origin is 1. And any such map can be written in the form f of x1 to xn. So these x1 to xn are coordinates on Rn. I'm trying to distinguish, each x means a point in Rn, and that's why I've underlined them. These are not coordinates of a single point, these are k-tuples of points in Rn. Here, these are the coordinates of a single point in Rn. And we can write this in the following form: fn of x, fp of x. So we can choose coordinates so that f takes this form, as here. This is just a consequence of the inverse function theorem or something quite elementary. Okay. So if f of, now let me I've got this problem of notation. Let's suppose that f of x, 1, x, n is f of x1, xn prime. So here are 2 points in Rn with the same image. Then x1 equals x1 prime, all the way down to xn minus 1 equals xn minus 1 prime, right? Because these coordinates, the first n minus 1 coordinates are retained, are on display, so they must be the same. So we can write x prime is x1, xn minus 1, xn prime. Or, in fact, preferably, a better notation is to write x equals x1, xn minus 1, and give a different name to the last coordinate. So we'll call this y. And now, our 2 points become, the first point will be x1, xn minus 1, y1, and the second point, x prime, will be x1, xn minus 1, y2. And this allows me to introduce k-tuples of points in which all the first n minus 1 coordinates are the same, and only the last one is different. Because if they have the same image, all the first n minus 1 coordinates must be the same. Okay, so when we've done that, if I can find the board rubber. Yeah, so let's change the notation slightly here. It's better to write n minus 1 y, and now that's probably a better way of writing, right? N minus 1 x coordinates and 1 y coordinate. That's helpful for this purpose. So, we get equations so let me rub this out. I don't really need to have all that there. Equations for dkf using iterated divided differences. That's what we did yesterday. So for d2f, the equations, assuming f has this form, I write fn, because the first n minus 1 must be the same. It's only here that I start to find anything more interesting. So fn of x, y1 minus fn of x, y2, and I divide by y1 minus y2. And I have to do the same for all of these last set of coordinates. So fp of x, y1 minus fp of x, y2 over y1 minus y2. Okay. Now, for d3 of f, I take these equations, those ones up here, and two more equations. I repeat the process. I write this equation, fn x y1 fn of x y2 over y1 minus y2. And now I subtract fn of x y1 minus fn of x y3 over y1 minus y3. So in other words, I've got this equation evaluated at x, y1, and also evaluated at x, y3, and I'm taking the difference, and that's divisible by y2 minus y3. So I divide, and we go on, we do the same thing for fp of x, y1 minus fp of x, y2 over y1 minus y2 minus fp x y1 minus fp of x y3 over y1 minus y3, all divided by y2 minus y3. Okay, and now for d4 f, I repeat the same procedure. Okay, so these equations, all this lot, and how many more? Well, I have to do the same thing again. So I've got, well, here I had how many equations? I have p minus n plus 1. And here I have twice p minus n plus 1. So obtained by repeating the procedure. Okay, so in fact, we find k minus 1 times p minus n plus 1 equations for dk of f. Yeah, because for d2, k was 2, I just had p minus n plus 1, k minus 1 is 1, And that's what I've got. For D3, k minus 1 is 2. That's how many I had, twice this number. And so on. So we get this large number of equations, but you can get them all. They're very easy to write down. It's quite simple-minded. It's quite a completely elementary process, what we're doing here. Okay, now, an interesting fact is that the dimension, that, let me just make a point. But that we're defining dkf in a certain space. We're defining it in the following space, in Cn minus 1 cross Ck. This is the space of points x1 to xn minus 1, because all the x coordinates had to be the same. If we've got k points with the same image, their first n minus 1 coordinates were all the same, so there's no point repeating them. The ones that might be different are the y's, y1 to yk. And now, the fact is that if f has finite codimension, finite AE codimension, then the dimension of dk of f is equal to n minus 1 plus k minus the number of equations for dk. So, how can you see that? I mean, that's not at all obvious. It's not a consequence of the equations, it's a consequence of the geometry. And one way to understand this, and this is, I leave this to you as a little calculation, if f has got finite codimension, then at most points where k points have the same image, that this image looks like the intersection of k copies of Rn meeting in general position in Rp. Because we're mapping Rn into Rp, and the most stable way for k points to have the same image is that at each point the map should be an immersion, and these k images should meet in general position. Okay? And now, if f has got finite codimension, then outside the origin, it is stable. That's a fact which I won't try to explain now, but that's quite easy to prove. And so, as a consequence of this, outside the origin, the dimension of the set of k-tuple points must be just the same as the dimension of the k-tuple points you find if you have k immersed n-dimensional planes meeting in general position in Rp. So let me just write this vaguely as this is the dimension of the set of k-tuple points in or when k n planes meet in general position in Rp. Most k-tuple points of f are isomorphic to this locally. Okay, so that's the argument that I tried to sketch. Okay. Okay, so this is a very nice fact that we can, if f has got finite codimension, we can define this space dk, and its codimension in here is, or its codimension, the difference between this dimension and the dimension of dk is exactly the number of equations. And another fact which we observed in our example yesterday. If F is stable, co-rank 1, then all the dkf are smooth or empty. If there are, I mean, it might, you know, if I have a map germ of multiplicity 3, I don't get any quadruple points, so D4 is empty. But the D3 and the D2 will not only have the right dimension as specified there, they're actually smooth. Now you can check this. You can check this by looking in the example that we had. You can prove it by observing that if you think about how to make it smooth by adding on suitable parameters and unfolding monomials, it's easy to do this. You can easily arrange for it to be smooth simply by adding on the right unfolding monomials. So if you look at the example yesterday, you'll see why that is. See why it's smooth and how you can always make that. So, conclusion, if F is finitely determined, or has finite codimension, then dkf is an isolated complete intersection singularity. So that's an ICIS. And these singularities are very well understood. This is the part of singularity theory that's most complete, ICIS. So now I want to draw another conclusion. Actually, what I've written here is slightly incomplete. Not only is it true that if F is stable, then all of the dkf are smooth, but one can prove, in fact, that this is equivalent. Yeah? If F is stable, let me get the logic a bit better. We're talking only about co-rank 1. F is stable if and only if all the dk are smooth. And actually, the same is true here. F has finite codimension if and only if all the dk are isolated, complete intersection singularities. I have to allow one further possibility. The argument here is that finite codimension is equivalent to being stable outside the origin. So what this tells us is that outside the origin, all the dk's are smooth, which means that they're isolated singularities, and stable outside the origin tells us what the dimension must be. What happens at the origin is not at all controlled. At the origin, anything bad can happen, and so we have to allow that they might be zero-dimensional without being isolated complete intersection singularities. But that's not a problem. The second conclusion is that, let's suppose that, so if F is a stable deformation, a stable unfolding of little f, we have this picture, dk of big F. Actually, I want to just add something. Remember, we write f of xu equals fu of x, and our parameter is u. Now, if I have a k-tuple point of big F, that means x1, u1, x2, u2, up to xk, uk. But because the parameter value is retained, then u1 and u2 and all the u's must be the same. If I have a k-tuple point, k points in the domain of big F having the same image, then the parameter values must all be the same. So, yeah, if x1, u1, if this is a k-tuple point, xk, uk, if this is in dk big F, then u1 equals uk, because of the way the parameter is retained in the fact that this is an unfolding. We hold on to the parameter. So, hence, there's a well-defined projection dk big F down to the parameter space CD, which is the space of the parameters u. And I'm doing complex geometry now. Well, I mean, this is still true. Let's just say k to the d. It could be real, it could be complex. And now, if I take u, so this is a map. What shall I'll just call this pi lower, or let's call this p lower k. Now this is a smooth space. This is a smooth space. Sard's theorem tells us that most points here are regular values. So if I take a regular value of this map, what I get is, well, the pre-image is smooth, and so it's a smoothing of the original dk of F. So if u is a regular value of pi of pk, so let's put that in here, then pk inverse of u, which is incidentally dk of fu, this implies that this is a Milnor fiber of the isolated complete intersection singularity dk of F. And that's what we saw. That's really what we saw in the picture that's hidden behind this blackboard. Okay, so incidentally, and a little corollary of this, if u is a regular value of all the pk for all k, then fu is stable. Because if u is a regular value of each pk, that means each of these is smooth. And now, if all dk are smooth, then it's stable. Okay? So what the purpose of all this, was just to go over some of the same ground that we covered talking about that example. So let me just put the example here again. This is smooth, this circle, for suitable choice of U and V. And each of these 6 points in D3 is a reduced point, is smooth, if you like. And so we have a Milnor fiber for D3 up here and a Milnor fiber for D2 here. Of course, I've drawn the real Milnor fibers, but the really strong information about the topology comes when we consider complex. And somehow, the image is assembled from the data that is present here by some means or another. So what I want to do now is explain in general how one gets that information, or how one manages that information. So, actually, it might be a good idea to say, does anybody have a question at this point? Because I'm going to sort of go off in a slightly different direction in a minute, and then come back to this in a minute. But if there are any questions, anything that needs to be cleared up here, then please do ask. Yeah. I can give you a reference. I'll give you a reference at the end. I think there's probably references in the lecture notes actually also. Okay, so quite a lot. In the example, you lose nothing, because that's one of the very few examples where all the homology of the complex Milnor fibers is visible in the real Milnor fiber. But that's very unusual. So that's why it's a good example, because you can kind of see in the reals everything you want to see. All right, so now I want to talk about, how do I want to introduce this? So let's look at dk plus 1 of f, dk of f, dk minus 1 of f. And now I'm just talking about any map f from x to y. In fact, it's going to be useful to assume that it's a surjective map, so the y is the image of f. And x could be anything, any topological space. This is completely general, what I'm going to talk about now for a little bit. So we've got a symmetric group action here, the symmetric group sk plus 1, and the symmetric group sk, and the symmetric group sk minus 1. And I've got this map pi k plus 1 and pi k. Pi k plus 1 forgets the last of the k plus 1 copies of x, and this forgets the last of the k copies. And now notice the following. Suppose I take sigma equal to k plus 1. That's a permutation in the S group sk plus 1. Then we have sigma of x1 xk plus 1. That's just x1 xk minus 1 xk plus 1 xk. Right? That's how the symmetric group is acting. It's permuting the copies of x And in this case, this permutation permutes the last two. Just interchanges xk minus 1. Now, if I map this by pi k plus 1, I get down to x1, xk minus 1, xk plus 1. And if I map down to by pi k, I get to x1, xk minus 1. So actually, after carrying out these two projections, the effect of interchanging the last two coordinates has disappeared. So just a very simple and obvious fact is that pi k composed with pi k plus 1 composed with this permutation k plus 1 is equal to pi k composed with pi k plus 1. Right? It's a very simple fact, but it has an interesting consequence. And that is the following. At this point, I have to pull a rabbit out of a hat. I can't really justify the following definition, but you'll begin to see why it's nice as we go on. And the definition is the following. We say that alt k h q of dkf. So this is HQ is the qth homology group of the kth multiple point space of F. And I'm going to define a certain subgroup of it. This is the set of homology classes, which I try to represent by putting a chain inside a box. So an ordinary homology class such that sigma lower star of C is the sign of sigma times C for all sigma in the symmetric group. So this is sigma is a permutation, so it has a sign, plus 1 or minus 1, an even permutation or an odd permutation. But sigma is acting on the space dkf. When I apply this permutation, it maps dkf to itself, and that induces a map on the homology of dkf. And that map's denoted sigma lower star. If you've got a continuous map, the thing it does on homology is the map lower star. Sigma lower star of this homology class should be either the homology class itself, if sigma is an even permutation, and minus the homology class if sigma is an odd permutation. That's what I want. This should be true for all of the sigmas. So that's called the alternating homology, or rather, it's called the alternating part of the homology. And now, I show you a very simple calculation which begins to show why we should be interested in alternating homology. So just a very simple remark. If C is in alt k plus 1 HQ of d k plus 1f, then let's apply this remark to it, this very simple fact. Then pi k lower star, pi k plus 1 lower star, sigma lower I'm particularly concerned with this particular permutation. because the two maps composing these three and composing just these two are the same map. But now this applied to C is minus C, because C is alternating. So when I apply these two, because they're linear, I conclude, the minus sign comes out, and I conclude pi k lower star pi k plus 1 lower star C equals, with the minus sign in front, is pi k lower star pi k plus 1 lower star C. Now, unfortunately, so twice pi k lower star pi k plus 1 lower star C equals 0. Now, I would like to be able to conclude from this that as a consequence, pi k plus 1 lower star C is 0. But of course, that's not true, or it's not necessarily true, because we're talking about, well, where is this? This actually, this is a member, we're in HQ of dk minus 1, aren't we? dk minus 1f. And the problem is that dk minus 1f might have two torsion. It might have non-trivial elements, which when you multiply them by 2, give you 0, like in P projective space. So that's a bit of a problem, because as we will see, it's very nice, or it will play a fundamental role in what we do, that we should be able to deduce that actually this is 0. I really want that to be 0, and we'll see why in a minute. So in order to be able to argue that, we replace this object with a slightly different construction. This is Viktor Oryunov who had this idea. He and I had looked at this construction, in fact, taking homology with rational coefficients, which did allow you to make this conclusion if we're working over Q, but threw away a lot of information. If you're working with rational coefficients, you've lost all the torsion anyway. So his idea was that we're going to replace this by something different. So let me explain what that is. So instead of the alt k HQ dkf, we consider, or we introduce, how shall I say, we introduce alternation, we introduce the SK action on the chain complex, on the singular chain complex. So you'll, well, I'm assuming that you know basic singular homology theory. So if you recall, perhaps I just fixed notation, Ck of x is by definition the set of formal finite sums n sub c, c, where c from the standard k simplex to x is a continuous map, right? We just look at formal sums of continuous maps from the standard k simplex into x. That's the chain group. And then we have a differential which maps this to c k minus 1x using the boundary. It's called the boundary map. And let's call this dk, delta k, and HQ of space x is by definition the kernel of delta k over the image of delta k plus 1. That's the definition of singular homology. So now we adapt this definition a little bit by, and in order to make use of this remark. And the idea is that we define CQ. Oh, I think I should have. I'm sorry. Yeah, I really want to use Q rather than K for the dimension. And so this is, I was indeed using it some of the time. And this is Q. So we're going to define the alternating part. So if Sk acts on, Sk acts on dk, so I don't need to say this. We define Cq alt of dk to be, or dkf, to be the chains C. Sorry, this should say C n sub, let's write it C n sub alpha C alpha. That's probably better. Where each n alpha, sorry, I can see I'm not writing things very clearly. Each n alpha is meant to be an integer coefficient. So we have a finite formal sum. Now, what I want are C in CQ of dkf, ordinary singular chains, but I want the action of the effect of the symmetry group action on them should be to multiply by the sign. So I have to use a slightly different notation. When you're talking about the action of a continuous map on a chain, you don't say lower star, you say lower sharp. Well, some people probably say lower star. But I want to distinguish between the action of the continuous map, this permutation, on chains and on homology classes. I use lower sharp for chains and lower star for homology classes. So I want sigma lower sharp of C to be the sine of sigma times C. Okay, so it just multiplies, it multiplies the chain by plus or minus 1. So let's have a look at, let's draw one here. Let's find an alternating one chain here. So in fact, it's not so difficult. So what I'm going to do, I'm going to draw a one simplex which goes round like this. So it's a one simplex, which just means a parameterized curve, the image of the unit interval, and it goes from this fixed point to this fixed point. And now I draw one going in the other direction. Okay, so let's call this, the red one is called C2, and the blue one is called C1. And now in the picture, you can check that C2 minus C1 is an alternating chain. Because the involution, what it does is it just simply swaps the circle over like that. So it takes C2 and puts it exactly where C1 is, and it puts C1 exactly where C2 is. The involution, that's what the involution does. But it also, since my chain is, so let's write it like this. 1, 2, that's the permutation, the unique non-trivial permutation in S2, lower sharp of C2 minus C1, well, that's C1 minus C2. Because, sorry, yeah, do I mean that? What do I mean? Am I getting this right or am I getting this wrong? So C2 is mapped to C1 what's happened to So I'm trying to get something usable out of this. C2 minus C1 is a cycle. It is a homology class because obviously the two have got the same boundary, and so when I subtract, I get 0. But I want so let's see, what's this? What's 1, 2 lower sharp of C1? Of C2? Well, that's, yeah, I'm sorry, I'm being a bit slow here. That's 1, 2 lower sharp of C2 minus 1, 2 lower sharp of C1. And 1, 2 lower sharp of C1, sorry, 1, 2 lower sharp of C2 is I just take C2 and I reflect it, and that gives me C1. So I've got C1, and then by the same token, 1, 2 lower sharp of C1 is C2, so I get C1 minus C2. Okay? Sorry, I vacillated because I thought this, yeah, okay. It's a very simple example. It works perfectly, actually. It's an alternating chain. Because when I apply this permutation, I change the sign of the chain. That's what I should do because this is an odd permutation. A permutation which is a single transposition. Okay. So we've defined the set of alternating chains. And actually, in this example, this alternating chain on D2 generates the first homology. The whole of the first homology here is alternating. Because when I act on the homology class with the permutation, then the homology class is multiplied by -1. If you like, this permutation is an orientation reversing permutation on S1. Okay. Actually, would be before I forget, exercise. Find an alternating chain on D3, an alternating 0 chain. Let's just write that. I'll write it over here. Okay. Anyhow, so I've defined the group of alternating chains, and one finds that the usual differential takes CQ alt dk of F and maps it to CQ minus 1 alt of dk of F. That's sort of obvious because since sigma lower sharp delta is delta sigma lower sharp. That's always true in homology. So we don't just get alternating chain groups, we get an alternating chain complex. And we finally define HQ alt of dkf to be the kernel over the image as before, but now in this alternating chain complex. So this is the kernel of delta from CQ alt of dkf to CQ minus 1 alt of dk of f over the image of delta from CQ plus 1 alt to CQ alt. same definition, the usual definition of homology, and we get this alternating homology group. So in this example here, actually the alternating homology group coincides with the ordinary homology group because the generator of the ordinary homology group is indeed an alternating one chain on D2. But that's not always true. Quite often they're different. But it turns out that these objects are the key to calculating the homology of the image. So, let me go through the calculation that I did before, and then you'll see why this is so crucial. I think I've got what, till 12:15? Okay. Is that right? 12:15. Yeah. That's fine. There's enough time. I mean, of course, I'm not going to get very far with this, but I just want to. I hope you understand the central idea. So remember, we had dk plus 1, dk minus 1, pi k plus 1, pi k. And remember that I said that pi k composed with pi k plus 1 composed with the permutation k plus 1, that's the same as pi k composed with pi k plus 1. We've already remarked on that. And from this, it follows that if C is an alternating Q chain on dk plus 1 of F, then, well, apply both sides, you get minus pi k plus 1 lower sharp of C is pi k lower sharp pi k plus 1 lower sharp of C. The same argument as before. And you conclude that twice pi k lower sharp pi k plus 1 lower sharp of C is 0, the same as before. But now, we're not in a homology group, we're in CQ of alt of dk minus 1 of F. Yeah, actually, this I didn't, let me just rub out the alt for a minute. I've taken a chain, it happens to be an alternating chain, but it's a chain, and I've pushed it down 2 levels, and so now it's a chain on dk minus 1. Well, now this is a free group. The group of chains is a free group. There's no torsion in here. So if twice this is 0, that means that this must be 0. So pi k lower sharp pi k plus 1 lower sharp of C is really 0. And this is the advantage of using alternating chains, that you have this interesting situation that if you go down 2 levels, you get 0. So let's just look for a minute at what we've constructed. I should make a remark before at this point. And that is that pi k lower sharp of the alternating chains of dkf is contained in CQ alt of dk minus 1 f. So that's not completely obvious, because the fact that this alt means that all these chains have some property under the action of the symmetric group SK, And here it means that all these chains have some property under the action of the symmetric group Sk minus 1. So it's a different symmetric group. But if I take a symmetric group element here on dk minus 1, that permutes k minus 1 copies of X. And in fact, you can then lift that to an element of the symmetric group of k copies, just leaving the extra copy fixed. And you can easily prove this statement. Okay, so now we have this following very beautiful situation. If I take dk plus 1, dk minus 1, I take c q alt dk plus 1 f c alt q minus 1. In fact, let's put q plus 1, q dk plus 1 of f, cq minus 1 dk plus 1 of f. So we've got this chain complex, delta, delta, and we've got this cq plus 1 alt of dk of f, and cq plus 1 alt of dk minus 1 of f, cq plus 1 alt dk plus 1 of dk of f, cq alt dk minus 1 of f. So we've got this two-dimensional array, cq minus 1 dk of f, cq minus 1 k minus 1 of f. So you've got lots of, you can sort of fill this diagram in at your leisure. But the important thing is we've got arrows going to the right and arrows going down. And we know from ordinary standard homology theory that the arrows going from the right, this makes a complex. We have a chain complex. At each level, this is the alternating chain complex. If I take the composite of two arrows, I always get 0. And that's why the kernel of each arrow is, where the kernel of each arrow contains the image of the previous arrow, why you get a homology group. But we've now observed that if you go down 2 steps, also you get 0. That's this calculation here. So that we've got a double complex. And the double complex, well, from a double complex, you can do a whole lot. This, unfortunately, is where the mathematics starts to get very complicated, because the way that one deals with the homology of a double complex is using a spectral sequence. And if you start trying to read about spectral sequences, it can be a bit confusing. There's a lot of combinatorics and a lot of detail. And I personally found it impossible ever to understand spectral sequences by reading textbooks about them. The only point at which I began to understand was exactly encountering this situation and really wanting to understand what was going on. So I won't go on about spectral sequences. Let me just say there is a spectral sequence, blah, blah, blah. If you want a formal statement of that kind, you can find it in the lecture notes. But what is more interesting is to observe how this alternating homology contributes to the homology of the image. And it uses, the fact that it does contribute to the homology of the image, uses nothing more than this statement that we have a double complex, but we can see it in concrete detail, and it's quite an interesting way to look at it, I think. So that's what I want to spend the last part of the lecture talking about. So I know this lecture is just jumping about and it's not finishing anything, and just introducing a few ideas and not developing them very deeply. But I hope that it gives you enough incentive to read something more. And, well, so what I should have said is this is a double complex, but I'm not going to write that. I'm just going to leave that there for the moment. Incidentally, I've said that that this is a double complex if I go down twice. So just a little exercise, just to see that you've understood. I mean, it's the same argument. If C is in CQ alt of D3, then F lower sharp pi, in D2, F lower sharp pi 2 lower sharp of C equals 0. So it's exactly the same argument as the statement that this is a double complex, but if we go down from D2 to X, just the domain of our map F, and then down to the image, once again, the alternating chains are killed. So you can easily check the same argument. Okay, so we're going to use this fact. So let's imagine that we're in this situation once again. So I'm sorry, the diagram is a bit compressed, but here we've got just a circle, and we've got an alternating homology class, this red minus blue, or blue minus red. And now I map this homology class down to here, down into R2. So consider. So I'm just looking at examples now. So I take the homology class C2 minus C1 in C1 alt of D2 of my map FUV in this example. And now I map it down to pi 2 lower sharp of C2 minus C1. That's in C1 of the domain, R2, in big capital C1. So one chain on R2. But actually, this is not just a chain, it's a cycle. Its boundary is 0, because the boundary of C1 and the boundary of C2 are equal. And so when I subtract, I get 0. So actually, let me rub out a little bit. Let me just write C2 minus C1 under delta goes to 0. And of course, it follows that therefore under delta, this also goes to 0. Because delta composed with pi 2 lower sharp is the same as pi 2 lower sharp composed with delta. If I go that way, it's the same as going that way. But now, that means that this is a homology class in R2. A one homology class in R2, because its boundary is 0. But R2 has trivial homology in dimension 1. So this is not just a homology class, it's a boundary. It's not just a cycle, it must be a boundary. So there must be some C prime here. There must exist a C prime mapping to delta. So this C prime must be a 2-chain. There must be a 2-chain on R2 whose boundary is pi 2 1 lower sharp of this alternating 1-chain. Because this alternating 1-chain goes to 0, so this exists as H1 of R2 is 0. Okay? But now we repeat. Now I apply, well, I don't have any more pi's, but I have F lower sharp. F lower sharp. So let's rub that out. So what happens when I apply F lower sharp? This was pi 2 1 lower sharp. That exercise up there said that if I apply F lower sharp after pi 2 1 lower sharp to an alternating Q chain, I get 0. So this gives 0. And now, if I apply F lower sharp here, I get F lower sharp of C, of this C prime, and that must map to 0. So what's happened is we've started off with an alternating one chain on D2, and we've pushed it down and pulled it back and pushed it down, and we find a homology class. We get a two-dimensional homology class in the image. We've used the fact that the first homology of R2 is 0. That's an assumption that we've used. So, well, of course, it's a true assumption. So the conclusion, using the fact that H1 of R2 is 0, we've mapped the alternating homology into the second homology of the image, Y, of our map. So that's the image, we called it Y. There's just a little problem that, well, it's not a problem because we can solve it. There were perhaps different choices of C prime. I just said there exists a C prime. Now, if I chose a different C prime, mapping to here, the difference between them would be a cycle. A C prime and a C double prime, well, the C prime minus C double prime would be a cycle and therefore a homology class. But actually, H2 of R2 is also 0, so it doesn't matter. But if we were dealing with a domain which was not contractible, which did have an H2, we wouldn't really be getting a map from here into H2. We'd be getting a map from here into the quotient of H2 of Y by the image of H2 of X. But because R2 is contractible, that problem doesn't arise. So we really do have a map here. So that's very nice. We get a homology class. In fact, we can prove it's not trivial in the image from this alternating homology class here. So that's given us one homology class. That's given us rank 1 in the homology of the image. And I want it to be 2 because I said at the start that this theorem that the rank of the homology of the image is the same as the codimension, and the codimension here is 2. So we need another cycle. So let's find the other cycle also, and we do it by almost exactly the same idea, but just that takes a little bit longer. So let's now we go to D3. So pi 2, pi 3. So let me take now a homology class C in C. How shall I write this? Well, I'm not going to write where it is, but I want this to be an alternating homology class on D3. So maybe I'll just write it C in C naught alt D3. So D3 of FUV. So I asked you to find an alternating 0th homology class. That was an exercise, and you can easily do it. So remember, a homology class on a zero-dimensional, well, a zero-dimensional is just a choice of points with the coefficients. So there are 6 points in D3. You've got to give a coefficient of +1 or -1 to each. And if you choose your point, the sign's right, it'll be alternating. So now let's assume this. Well, of course, since D3 is, well, since we're talking about a zero-dimensional homology class, then when I apply delta, I get 0. So it's not just a chain, it's a class, a homology class, it's a cycle. It's an alternating cycle. Now I apply pi 3 lower sharp, so I get pi 3 lower sharp of C. So it's still an alternating cycle on D2. Now let's assume that H2 H naught alt of d2 of f uv equals 0. We'll come back to that assumption in a minute. It's correct. It's true. It's true. That's sort of easy to see, because if you just think about the definitions, it's easy to see. But let me not worry about that for now. Let's continue. So under this assumption, that means there's an alternating chain. Maybe I'll call this C. I don't quite know what label to use, because all right, let's just call it C prime. So by going one to the left, that means I'm increasing the dimension. This is a one chain, and it's on D2, which maps to here. It must exist because this alternating homology group is 0. Because, of course, this goes to 0 by the commutativity of this little diagram. So now we've got an alternating one chain which maps to this alternating 0 chain on D2. But now if we apply pi 2 lower sharp of C, of course we get, this is pi 2 lower sharp of pi 2 lower sharp pi 3 lower sharp C. That is 0, because we know that go down twice you get 0. So this C prime, pi 2 lower sharp of C prime, goes to 0. So it's a cycle, and it means it represents a homology class. Now we're in R2. The first homology of R2 is 0, so there must be a C double prime. There must exist a C double prime mapping by delta to pi 3 lower sharp of C prime. And now, if we apply F lower sharp, we get F lower sharp pi 2 lower sharp C prime, and that's 0, because going down twice gives you 0. And so if I apply F lower sharp to C double prime, and then apply delta, I get 0. So F lower sharp of C double prime is also a homology class in the image. So under our assumptions, about vanishing of H naught alt of D2, FU, etc., because I want to allow more arguments of this kind, in more examples, and one has to make certain assumptions. We have a map which goes from H naught alt of D3 of F UV to H2 of Y. So previously we got a map from the first alternating homology of D2 into H2 of Y, and now we found a map from the 0th alternating homology into H2 of Y again. And that's where the two cycles in the image come from. One comes from triple point, and one comes from the alternating cycle on D2. So essentially, in a very vague and incomplete way, I've tried to convince you that the alternating homology gives rise to two different homology classes in H2 here, and that's the correct statement. And in fact, there's a theorem which one proves using a sort of spectral sequence that comes from that big double complex that I wrote up earlier, which is a very nice statement. Let me end with this statement. So if f from Cn naught C n plus 1 naught is finite codim, co-rank 1, and Ft is a stable perturbation, then Hn of the image of Ft is isomorphic to the direct sum of the alternating parts Hn minus k plus 1 alt of dk of Ft. So, in fact, the alternating homology of each of these multiple point spaces contributes, just as we saw in this example. We saw H1 of D2 and H0 of D3 contributing to the homology of the image. But there's a general statement here. Now, I said that to make these calculations, we had to make some assumptions about these things vanishing, these groups vanishing. And what justifies this assumption and helps to prove this theorem is the fact that each of the DKFs was the Milnor fiber of an isolated complete intersection singularity. And from that, it follows that it only has homology or only has alternating homology in one dimension. It only has alternating homology in middle dimension. And all the other alternating homology groups vanish. And this is particularly crucial because it means that each of these assumptions like this, which allowed us at each stage to say, well, if this went to 0, there must be a chain back here which maps onto it. That's what allowed us to make this argument. Those assumptions are justified. And this is because each of these DKs is a Milnor fiber and only has homology in middle dimension, apart from the 0th homology. And if we take alternating, then the alternating homology really is only in middle dimension. So all of the groups that you want to be 0 are 0, and this argument always works. Okay, so this is a theorem that was proved by Goryunov and myself. But then Kevin Houston, in his thesis, proved a much more remarkable statement that the same is true without the hypothesis of co-rank 1. Yes, yes, so theorem. This is true without So what he showed is that the alternating homology of all these multiple point spaces is still concentrated in middle dimension. It is not anything like so obvious as it was in the co-rank 1 case, because in the co-rank 1 case, each of these spaces was a wedge of spheres. It was homotopically a wedge of spheres because it's a Milnor fiber of an isolated complete intersection. So one understands the homology very well. But in the case of map germs of co-rank greater than 1, actually we know almost nothing about the multiple point spaces. They're certainly not complete intersections. They might have isolated singularity, but even that's not clear. And they're not, so the multiple point spaces of the stable perturbation are not wedges of spheres, and they may have homology in many different dimensions, and in fact they do. But the remarkable thing is they have alternating homology only in middle dimension. That's what Kevin proved in quite a difficult proof. So anyway, that's the end of this topic. We don't talk about this topic anymore. Thanks very much.
Questions? Please wait for the microphone.
Can you state mathematically what you lose when you go to the real case? There is a mathematical statement where you express what you lose.
What you lose? Well, if you go to the reals, then you no longer know that the homology of these Milnor fibers is concentrated in middle dimension. Because the Milnor fiber of an isolated complete intersection singularity is homotopically a wedge of spheres if you take complex. But if you take the real part, it may have homology in other dimensions. So the thing becomes much more complicated. It's very hard to make a general statement. I mean, there is always a spectral sequence, but what you don't know is that it will collapse, as it does in the complex case, at E1 or E2 or whatever it is.
Are there case studies of the real case where you can observe this?
Yeah. Yes.
Any references?
Probably in the papers. I think there are some references. Yeah. But I think it wouldn't be very hard to cook up some examples.
And the hypothesis of finite codimension is essential anyway.
Yeah, yes. I think in your theorem it's essential, isn't it? What do you think? The hypothesis of finite codimension is needed for this collapse? Yeah.
Miriam has some announcements, and I would like to say also two things. First of all, who ordered? I have the notes, the lecture notes here for those who ordered. As notas estão aqui comigo para aqueles que pediram. Por favor, peguem comigo. And also, if you have an accompanying person for the barbecue and the dinner conference, please let us know. There will be, you could put the name on the desk, ok? Se você tem uma pessoa que vai acompanhar você para o jantar ou para o churrasco, dá um nome para a gente. Não, para a semana que vem. Ah, quanto que é? Ah, não. Para a semana que vem. The conference dinner and the barbecue party next week. Okay?